Hello and welcome to the 10th tutorial of this course, Reinforcement Learning. I am Mohit Kaur, a PhD student at Indian Institute of Science. So today it will be mostly implementation-based tutorial. We'll implement algorithms which are based on neural network function approximator. So precisely, we do implementation of uh, DQN algorithm, deep Q networks. Then we'll do TD policy evaluation. And then we'll do actor critic. Okay, so let us first revisit DQN algorithm. What is deep Q network? We'll look at it. I mean, recall it. So this Q network is basically a neural network which approximates the or tries to approximate the uh, Q function. What is Q function? Q function is Q. So map from state action space to real numbers such that QSA is expectation of the rebound sum of rebound equals to 0 to infinity gamma raised to T or ST AT. Given is 0 equals to S and A0 equals to T. So this is the Q function, and we try to approximate this Q function using a neural network. And uh, how do we try to approximate? That is the main discussion next. So we know that Bellman equation for Q function is the following. Okay, so I made a mistake here, definitely. This is max over all policies. Policy looks denoted by capital Pi on the set of all policies. And here expectation is taken with respect to the policy. So it means that action 80 is taken according to the policy Pi and the state ST. So the Bellman equation for, we can also denote this Q by Q star. So Bellman equation is Q star SA is equals to the current reward RT or R of STAT S and A. Sorry. So this is STAT RT plus gamma times Q star ST plus 1. Okay. So if we would have known this Q function, Q star function, then you would have taken action A according to, so we observe is state ST, and whichever action is maximizing our current Q value, we would have taken that particular action. But we do not know Q function. So the idea is we'll keep on trying to estimate as accurately as possible from the samples we are collecting. And uh, as we are more sure that this our Q network is, uh, uh, I mean, approximately very close to true Q value function, then we give more probability to those actions which are maximizing the Q function at current state. So we use the TD idea, as temporal difference idea. If we can recall, we discussed that next. So this is the network Q unit. So uh, it outputs your Q values, and if you give input S and A, ideally it should show you the true Q values, right? So when you feed, so this is ideal, not ideal, but let's not write this Q unit. Let's write Q star. This is the function. So this is not the neural network approximation. Let this one is your neural network approximation. Write it Q net. And that is, say, parameterized by some theta. So that is throwing you some QAC parameterized by theta. Now there must be some difference between Q star and A. So the error, so we can write here STAT. That is no problem there. STAT. So we are talking about only TXI. So the error here is, say, if we are going with the square, so the error is Q star STAT minus Q STAT at theta. At the square of this quantity. Now, if you would have known this Q star STAT, then it was done, right? But you do not know that. So what you do here, you implement the TD idea, that is temporal difference idea. What is that? So when you have this STAT available, you also have taken the action AT, and you have got the next state ST plus 1. So this ST plus 1, if your this network was correct, then you would have taken the action which is maximizing the Q value at state st plus 1 at time t plus 1. So your error, so you can write that as TD error. So Q star ST80 you don't have. Instead, you have this quantity. ST plus 1. Now we maximize the action, right? I maximize the Q function. Minus. So here, do we use the same network? I mean, here there is some theta, and here is some theta. So do we use same theta for this? The implementation is done little bit different than the theory. Uh, so what we do is we fix the theta for some time. Then one thing remember, when you have this theta vary, so your target is also varying, right? So in supervised learning, if you recall, so you have a set of data points, the which is the tuples xt, yt, where t running from some capital. Now here your target is yt, and you have a neural network approximator f parameterized by theta that is taking xt. So f theta xt is trying to be as close as possible to yt. Now this yt is not getting generated on the go, and it's not basically varying. So you have the data, and based on the data, you have a set target. So from t equals to 0 to here t is different. So this is for data. So let me write this in. So this data set is yeah, this data set is fixed for different iteration of the training. So the target is not moving. But here the problem is your theta is changing. So when you do one iteration of this, your theta will change. And basically in the next iteration, when you will use the same, if you will use the same transition, your target will be vary. So it's a moving target thing. So that's one of the main problem here. So in practical applications, what we do is we fix a theta at say iteration n naught. We fix the theta, say theta target. Then from m naught to time n iteration n1, we keep this theta target fixed and vary the other theta. So this theta is changing. This theta keep on changing. And then after n1, we again update the target theta with the current theta, and then we run it for some time. So that's how it works typically. And also another application related thing is replay buffer. So what's the idea behind that? So here you are collecting your samples at different times. So uh, after plugging till time tau, data set data set is st, at, st plus 1 and art. And this is running from t equals to 0 to tau minus 1. So here, if you see this, if you go with TD, classical TD error update. So at time t, your error is this at time t. But this is very inefficient. If you use only this sample at time t, you're basically neglecting all the past samples. So what we can do instead, we can store this uh, store this data, and then while updating the theta, we can sample this uh, this data ST, ST plus 1 and RT randomly from this data set and update our Q functions. So that is a quite necessary and intuitive solution to this problem. Okay, so now we are moving to this Jupyter notebook environment and try to code this DBQ network. I hope the screen is visible. Okay, so this is the Q learning code. So we can copy certain things from this definitely. You can copy the MDP. So we need some libraries for coding this uh, neural networks. So we need to define a neural network here. So unit is the name of the class. So this I'm designing a two-layer neural network, but there is a hidden layer, which is so I'm keeping a hidden dimension as 48. By default, this will be if I do not pass any. So here, depending on how many actions and how many states are there, will so we'll feed the state and action uh, to the Q network. So here in this MDP, we are writing this state and action uh, as a number, integer from 0 to ns minus 1 and 0 to n, sorry, yeah, 0 to n minus 1. So should we write that? Uh, I mean, when you're giving the input to the Q network, should we keep that number like that, or should we do something else that we need to decide? So one possible way could be to design a one hot vector for state and one hot vector for action, and then put that uh, in the input. But that is very inefficient. Here we have 10 states, 10 actions, I think. So totally it will be a 20 length, a vector with 20 elements. But if you have to consider uh, state action space with, I mean, say if the state space is continuous or action space is continuous, then you can never do that. So we'll go with one input for state, which is the number, and one input for the action. So the dimension of the input layer will be 2. So and there is the output layer. So what will be the input size of the output layer? That will be hidden dimension. And what will be the output of this network? That will be just one Q value, right? So it will be one. So these are the layers, and then we have to define the how this. So one function which is called, generally people name it by forward. So where you will input the state and action, it will throw you out the Q values. So self uh, pardon, forward. So AC is basically concatenated state and action. And so can write Y stop. First we'll give the input to the hidden layer, hidden self body, self. It takes action, state action here, so S3, and then we update the out, which is self dot hidden. So here there could be one problem, that is you recall that whenever we have to do that TD target, you have to take maximum over all actions. So here the problem is whenever you will have to take maximum over all actions, so you have to send every pair. So you have ST plus one, which is when you have it's just a state. And for ST plus one state, say that state is one, and there are 10 actions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have to send one times in the cube network, then 1, 2, then 1, 3, up to 110. So these 10 pairs of state action you have to send to the queue network, and then only you can evaluate all this and the max of this values. So it's highly inefficient according to me. So what we can do is, and the output could be of size 10A, how many actions you choose, and yeah, basically then you are trying to model for given state what are the Q values of the corresponding actions. So now you can put one as your state variable. So you just pass the state number, and you'll be thrown out with all Q values for all actions corresponding to that state. So let's write this as is or SL. And then this is the output layer, which take outs. So we have not added non-linearity. So here we can add non-linearity to. So then we have written the class. So we now have to instantiate the uh, networks, which is say QNet small, and there you have to instantiate this network. So here we create two copies of this QNet. One is the QNet, which is there, and then we can create another copy target where at times we'll copy the model parameters from QNet to the Q target. So Q target is again QNet, and Q target. So this next step will be basically copying all the model parameters to uh, to the Q target from QNet. Dot static QNet dot state. And then set this Q target dot requires grad. So this we are not doing this gradient descent on Q target, right? That is we are keeping fixed for different time intervals. So we are not learning that, right? We're learning QNet. So that's why we do not compute the gradient of on this target network, and we keep this parameter as set as false. Okay, so this was the part of someone is not defined. Events pass any as well. So NA is for this example, NA is what? Okay, so this is created randomly. So NA is something which can be passed. So yeah. So let's keep NA equals to 10, and fine, this should be great. So we have formed the uh, Q network, and we have copied it, and fine. So next thing is basically constructing this replay buffer. So how to do that? So class replay buffer. So here is one problem. If say we have uh, this uh, buffers, we have not defined the buffer size, upper limit, how many data points it can store. So what will happen is when say we are running it for millions of time steps. So when it's towards the end, it will be very slow because it has to fetch and load uh, huge amount of data from memory. So what we can do is we can limit the size of the replay buffer. Also, there is another reason. So initially, the algorithm will explode a lot, right? Because as you have seen in Q learning, so you explore with epsilon probability and take greedy action with 1 minus epsilon probability. And initially is your epsilon is kept very high and gradually it decays. So initially you explore lots of suboptimal actions, and then gradually you sort of settle at optimal or near optimal actions. So as time progresses, if you keep your old samples, then it's not very efficient because on those samples are not really helping you. Rather, if you keep the recent samples more and put emphasis on this while training the Q network, so you can differentiate with your near optimal actions as well. So if both actions are near optimal, but still one is better than the other, if you see those samples more, you can differentiate this type of samples. So that's the main idea why we keep buffer size limited. So we it's, initialize this function, sorry, class buffer size. So buffer size we can specifically keep it int. The next operation you can do is you can add samples to buffer. So if the buffer size has reached already the buffer at the limitation of the buffer size, that is this variable, then we have to delete some data. So we can delete the first data, which so it's like first in, first out. Uh, so it so we will delete old samples. That's the idea I have told. So if length of the of is equals to self dot buffer size, then we pop out one the zeroth position. Next thing is you have to sample from this buffer at times. So the sample function will also take the input, which is the sample size, how big sample we want. Sample text. So I will find the sample size. But then it can happen that the current buffer length we have not say my sample size is 100 and we have currently didn't uh, gather 100 data points. So we have to update the sample size as sample size equals to mean of mean between the length of the buffer and the sample size. You may not need that, maybe say our sample size is 100 and we are first starting to train this network at 200, time index equals to 200. So in those cases, it will not be unnecessary step, but still. So you have to import another library called random because we use the function. So then what we can do is so each sample has four components, right? Current state, actions, rewards, next state. And there could be another one if we are looking for episodic tasks. If the episodic task has ended, so the end of the episode could be one variable. So you're including that. So you can so we have in this list we have each of these five tuples, and what we are going to do is for all the samples we are collecting only the states, and then all the samples we are collecting only the actions, and the next state, then the rewards, then the uh, completion of the episode. So next we are going to do that thing. So I0 or mm, I tens. Similarly, actions. So let's just paste it four times. Next will be actions. Next will be next states. Then rewards. Then dunks. Then we need to do another thing, which is basically these are lists. So from lists you have to convert to Torch tensors because that's the only format this neural networks made with Torch libraries accepts. So states is basically Torch. So this say the data type we have to set. Uh, so this thing we have to do for all the five things. Then we return this entire thing. Okay, so then we have this optimization step. But before that, before going there, I need to take a break for 5 minutes. Welcome back. So let's begin where we have ended. We have completed this replay buffer, coding of replay buffer. Now we have to design the optimization of this of the queue network. So for that, what we can do is restart playing this for say some k number of episodes, uh, and for each episode of say some length each. Each time we start the episode, we uh, set this uh, set the sorry, reset the system or the environment, and then at each time we pick a sample, we uh, collect the samples, we add them to the uh, replay buffer, and then we keep on doing that. At the end of the uh, episode, we basically go to the optimization part of it, and then we sample uh, certain states and make it a sample some data from the replay buffer, and we create the data set and just do the optimization for certain time. And then again, we go back and play some more. Uh, and we keep repeating this process. And how we take actions. So uh, you can take action based on our current queue network, which is available before starting of the episode, and with epsilon probability. So how we design the epsilon, we vary the epsilon. That is also another question. So first we write the optimization part of it, and then we go to the manual. So Gamma, I think we have not defined it. Points 99. So for optimization, we need to instantiate an optimizer. So we can use the very popular Adam optimizer here. Optimize is the so there has to be a learning rate. Let's keep it um, 1. And there is something called SLNDK. So let's keep those things at default value. So these are basically your samples, and we're feeding the samples with the optimize function. So the computation of target is the first thing. We have the target fixed, and while computing the target, we should not compute the gradient. So Torch has very uh, nice thing to do that. So whatever we'll write inside this, uh, inside this block, for those operations, gradient will not be computed. So this is using the target for all actions. Okay, feed next state. And that will basically generate queue of next state at different actions. Then target at max action, which will be nothing but Torch. So instead of this MDP, we can use inbuilt MDP in gym environment. So we had another function for So there are some errors I'm getting. So these are sort of uncalled for and unforeseen. Probably I'll try for some time to resolve this error, and then if we do not succeed, then I'll try it offline and I'll end today's tutorial. So we have this algorithm running. There are some difficulties which caused this. So I'll upload this. This is already actually uploaded uh, in the notes section. So there is that folder called codes, and if you go there, you'll find this file dqn.inv. Uh, so there you will have running code of dqn. And I had planned to do for TD learning and also after rating so that I can get time today. So there is insufficient time remaining, 20 minutes around. So what I'll do, I'll try to code this offline and then upload it in the same folder. So that was all for today's tutorial, and we'll see you in the next tutorial. Thank you.